Hello, everybody. Welcome to this second meeting of the new series of the DI online seminar. So as usual, we are going to have two speakers today. So the first one is going to be Tanja I Schindler from the Jagiellonian University in Krakow. And the title of her talk is Properties and Limit Laws of Dynamical Systems with Two Infinite Components.
Okay.
Tanja.
Thanks for introducing me. And let me first share.
Let me also add that in case you have questions, you can ask by yourself or use the chat.
Okay, I think it should be visible now.
Yes.
For everybody. Thanks. Okay. Well, thanks again for introducing me and thanks for inviting me. And I think we are also not such a huge group today. So even if it's live and if you don't feel too intimidated, then just ask in the middle. So, well, I mean, actually, I wanted to do a lot of other things in this talk, but I was ill the last couple of days. So I said it's somewhat expository. Now it's only a little bit expository because I didn't have time to do more. Anyway, we first introduce some system with at least one infinite component, and I will explain what I mean with an infinite component. And then I will go to two sets which have more than one infinite component. Either it's a system with dynamically separated sets or a system with an infinite measure and a non-integrable observable. And I say something about the properties for these systems. And in the last section, just shortly, I will say one thing about the relation between the two last settings. Okay, so let's start with some systems with one infinite component, and in general, we consider T as a transformation which is conservative, ergodic, and measure preserving on a sigma finite measure space. We don't, at the moment, we don't see anything if it's finite or infinite. Just to say what conservative means in case you haven't seen that. Or first, what is ergodic? In case it's an infinite measure, it means basically the same that if the pre-image of some set is contained in the set itself, then the measure of the set is either 0 or the complement is 0. And it's conservative if it's non-singular, meaning that the pre-image of some set is a null set if and only if the set itself is a null set and it has no wandering sets, meaning that after some iterates, the at least some part of the set returns to its origin, so the intersection is non-zero. And for the following, we assume that we have an observable which maps X to the reals, and we restrict ourselves to the non-negative reals because I don't like writing absolute values. And we define the Birkhoff sum in the usual way that we take F composed to the J's iterates of T and sum that up. And when do we speak about infinite components in this talk? So the first system will be the system that we have a non-integrable observable. So our infinite component will be that we are non-integrable, and in the second point we say that okay, our infinite component will be that our system has an infinite measure. So this is our infinite component. So it's basically me who actually says this about components. So our first setting is that our system is actually a probability measure, and it is and our function f is non-integrable. And in this case, Birkhoff's ergodic theorem, for instance, doesn't hold anymore. And by a theorem by Aaronson, we have that Well, if we look at this Birkhoff sum and divide it by a norming sequence, then either almost surely infinitely often we underestimate or we overestimate the sum by this norming constant which doesn't depend on x. And however, under suitable conditions on the function f, we can get a trimmed strong law, meaning that if we, for instance, remove the maximal entry of the Birkhoff sum, then the remaining sum behaves asymptotically like a constant. And here are some references. So, for example, one example where these things hold true is the situation that we have the regular continued fraction entries. And in this upper case, these results actually also coincide with IID random variables. And if our function f has heavier tails, meaning that the probability that we get large events is even larger, then trimmed strong law like this might not hold anymore, but we might have to remove more large entries, like even a number of entries which depend on n, for example, something like log n many. And in some cases, it might also be the case that we have the same distribution function as in this case, but we have to remove still more large entries because the system simply doesn't mix it nicely. So we have to remove some clusters of large events. Okay, so much about the almost sure convergence. In terms of the distributional results, there is no central limit theorem. For instance, of course, you would need L2 observable, but under some conditions, a stable law can hold. And well, these references I give here are certainly not all not exhaustive. As I said, I didn't have too much time to get make it too expository. So, but depending on the system and on the observable, one might get under these conditions a stable law. Now we go to the second situation that we have systems with an infinite invariant measure, which means now we look at the situation that our measure is infinite, but still sigma finite, as we said at the beginning, and f might or might not be integrable. But for example, if it's integrable, then again we are in a similar situation as we were before, that if we have a norming sequence, then no matter how this norming sequence look like, we either infinitely often underestimate or overestimate the Birkhoff sum by this norming sequence. And now the question is, okay, we have seen before this trimming method. Can we get a strong law in this case also for under trimming? Because, well, we had here the same situation, but well, trim L1, for instance, means we could have observables with just bounded, and so just removing the largest entry would not really change much in our sum, but we get a related statement. And I just want to give you some notation before we can really do anything. So if we have some finite measure set and we actually norm it to a measure set of measure 1, then we denote the first return time by if we iterate t to be the time it takes until the orbit gets back to E. And almost surely this first return time is finite, so it makes sense to introduce this t. And so we can also define the induced map, which means we basically iterate t so long that we are getting back to E again. And then we define the level sets En as a measurable partition of E, and take the union of all those sets such that the return time is larger than n. So we basically take a union over these sets En. And well, before we basically had a standard notation, but now we look at some more generalized or well, more abstract systems. So we look at the longest excursion out of E beginning in the first n steps. So well, this is basically written here in this notation, but what do we actually mean with that? So if we look at example, in red we have all those points where we actually hit E. So we start outside E, we might get the end back into E, we sample along and well, we are back in E, and then we reach our end point. And then we continue, and well, in this case, we are actually outside E at the end point, and we continue sampling, and well, in this case, 3 steps later, we are in E. And now we ask, okay, what is the longest excursion? And in this case, it would be here the last excursion. But of course, this does not have to happen always in the last excursion. It could also be that we have the picture like this, that we have a very long excursion before n, and then at n we have a very short excursion. And so our m would be, in this case, 5 and sampled very early. And just for completeness, where does this very weird number come from? If we denote by REN the number of visits to E up to time n, so we can basically denote it as a Birkhoff sum of the indicator function E composed with T, then this quantity m can be seen as the maximum of the return time composed with the induced transformation if we sample from 1 to this quantity En. So just to tell you that this quantity somehow makes sense. And now if we look at our system as before, which is like, okay, our infinite measure set, which is sigma finite and Gothic and conservative. And well, I mean, the conditions are a little bit technical, so I decided, since I wanted to have it a little bit expository, to not give all the conditions precisely, but they can be looked up in the paper. So we need some mixing properties on the induced transformation TE, which is actually quite a strong mixing property we need. And additionally, we need a condition on the growth rate of the super level sets. So, or basically decay rate. So they can't decay too slowly. And however, if we have those two conditions, which are only a condition on the system, not at all a condition on the on our observable f. If we now look at this observable f, we can see, okay, no matter which integrable observable we have, we get a strong law of large numbers if we just add additional summands. So instead of the situation where we were looking at trimming, here we have to add additional summands, namely m, this quantity m many. And then the statement is basically independent of f. The f appears on the left-hand side and the right-hand side, but also this norming sequence does not depend on f, or basically one could divide by integral over f d mu and has convergence to 1. And alpha of n, the norming sequence, is directly given by the super level sets. And some remarks about it. So the sequence alpha of n coincides with the constants which we get from a weak law of large numbers. So what we do here to truncate this sum is maybe not so much of a weird thing, or we don't truncate it too much. So we still stay in what we would expect to get as a norming sequence. And these conditions 1 and 2 are kind of necessary that the strong law of large numbers holds under trimming for the induced system. Kind of necessary means that if we relax one of those conditions, then basically we find examples where the trimming statement doesn't hold anymore, and which means, on the other hand, that we wouldn't get a statement like this for the original system. Okay, and well, I said something about the growth rate. We need some rate. So this condition 2 is, for example, fulfilled for any decay rate like the case power of a logarithm of n over n, which also means we could have here something like the zeroth power, which is like something like 1 over n. So I said these super level sets, they can't decay too slowly. Also, in this case, of course, there are lots of distributional results. Again, we don't have central limit theorems, but of course, we could have some, for example, some stable laws for the return time. There is certainly also a gap where I could fill in a lot of other things where I simply didn't have time. So everybody not mentioned here is welcome to be angry with me. Sorry. So next I will say a little bit about systems with dynamically separated sets. And I just want to say...
Tanja?
Yes?
Sorry, before you change topic, can you give some examples of systems where your results apply, just to have an idea?
Yes, I mean, you could have something like Liverani-Sassol-Vajenti map with the right alpha. I think it has to be something like alpha equals 1. And then, well, any observable which is integrable.
For Bonanno as well? Or?
Yeah, exactly.
Okay, thank you.
Yeah, thanks for asking. Okay, so let's now look at these systems with dynamically separated sets. And what do we mean with that? And this is now one of the first examples where I would say, okay, now you have basically two infinite components. And again, we assume that our measure is infinite, and we consider two subsets of X. Well, I mean, they should also be measurable. And we assume that if we start at some point X in A, and iterate X, and iterate T, and if this iteration ends up in B, then there exists some k between 0 and n such that the case iterate of T on X ends up in the set Y. Basically, and then we say that these sets A and B are dynamically separated by Y with respect to T. And well, in simple words, this means if we have an orbit of T to pass from A to B or vice versa, it has to pass through Y. So okay, and we are basically interested in systems where we have sets where A and B are both infinite and Y is finite. So our basically what I would call as components are that A and the components would now be this infinite sets A and infinite set B. And so, for example, one natural question for such system to ask would be to compare the occupation time of A compared to B. So how long on average does the system spend on A and how long on B? And well, there are also a lot of results and where one gets some Arcsine or Darling-Cut laws basically answering these questions. And I just want to show you what examples are there actually for such systems. So the easiest example one could look at is the Boolean transformation given here, which is invariant with respect to the Lebesgue measure. So of course it has an infinite invariant measure. And if we look at some iterates, basically one always has to pass through this interval -1, 1 here. So if we start on the red set A, we iterate a couple of times, fall into the middle, and okay, well, this I wanted to look at a little bit extreme, so I did a lot of iterates, but of course, I mean, you could also fall basically into -1 million, and then you'll stay a very long time in the blue set B. And here the tails of A and B have the same size, so this is maybe not the most interesting system to study, but still one can do it. And well, basically standard examples for these systems piecewise expanding interval maps which have two indifferent fixed points, something like given here. So like the left side could be seen as Pomo-Menville, but then it's basically mirrored branch also on the other side. And you always have to get somewhere in the middle to get from one system to the other. And well, let's see, generalizations of these maps have recently been studied in these papers. And here, well, also in this preprint by myself. And here we don't only look at piecewise expanding interval maps, but we also look at maps where we could here at 0.5 could have a unbounded derivative. And this unbounded derivative, so these maps might look somewhat like this. In this case, they might not always have a infinite measure, but sometimes also a finite measure. But basically, what is happening if we have an unbounded derivative? It shrinks the infiniteness given by the indifferent fixed point. I mean, I didn't mention that, but I mean, this behavior basically has also been studied by some other people. I mean, since Christodoro is here with only one of those branches. And so if the derivative is too infinite, say, then this might mean we actually get back to a finite measure. But if it's not balancing it out, we still keep it being a finite measure and basically still in this set. And well, the focus of these works mentioned here more on the finite measure case, but basically what's done there gives the basis to also look at infinite measure cases. And well, the mixing properties compared to the standard piecewise expanding interval maps with an indifferent fixed point for these maps then might still be different. And then some of the limiting results studied before might be different. Sorry again. Okay, so I said, okay, these are is one of the systems with dynamically separated sets. With two infinite components, I want to say something about another system with infinite components. And namely now we have an infinite measure and a non-integrable observable on a finite measure set. So, okay, again, we have an infinite measure, and then we assume there exists a measurable set E of finite measure such that if we integrate over E, then we get infinity. And so the first question is if we can see something about almost pure convergence. And so we can just look at one example, namely the backwards continued fractions. And I might just say a little bit more about them. Okay, this is what we have as backwards continued fractions. What do I mean with that? Okay, we don't always look at animals, but let's see why we actually call them backwards continued fractions. If we compare them with the regular continued fraction expansion. So in the regular continued fraction expansion, we would always have a plus here. But now we basically have a minus. This is the only difference we have in this system. However, this like a small difference might mean a large difference for the behavior of this type of continued fraction entries. And where I just want to say these continued fractions were first studied by Renier. So they are also quite old object of study. And well, these entries, dn, can be generated as in the classical continued fraction example with the transformation given here and observable. So we compose the observable with the n minus first iterates of the transformation and then get these backwards continued fraction entries. And now the question is, can we actually say something about these entries of the backward continued fractions, or of the sum of them, which is basically the Birkhoff sum? And well, just to say something about some comparison with the regular continued fraction entries to see why these continued fraction entries are actually called backwards continued fraction. So if we look at the regular continued fraction and the backward continued fraction, we see that well, the transformation is just mirrored at 1/2, and the observable is more or less also just mirrored, but well, for some technical reason, it has to be shifted 1 up. And yeah, this is basically what I said. So the observable and the transformation can easily be written vice versa by the regular and the backward continued fraction. And well, as said, they look very similar, but they behave actually quite differently. And in particular, we have that, well, this regular continued fraction expansion is invariant with respect to a finite measure, whereas the backward continued fraction entry is invariant with respect to a measure that is infinite. So basically, now summarizing things, we are exactly in the situation I described before. So our measure is infinite, our f is non-integrable, and it's even so that if we look at the set 1/2 1, if we this is a finite set with respect to this infinite invariant measure. If we now integrate over basically this set, then our observable is still infinite. And okay, let's now see something about a general result. So we consider our setting as before with now it's not the backward continued fraction entries anymore, but basically any infinite measure preserving ergodic system that is conservative, and G is any observable mapping to the non-negative reals such that it's its integral over a finite measure set is infinite. And then, well, we have again some conditions which I don't state precisely, again some mixing properties on the induced transformation TE, some properties again on the growth rate of the superlevel sets, and some regularity conditions on G. Basically, G has to be constant on some partitions of the partitions generated by the induced transformation, and it has to be constant out of E. And then I give a precise, more precise condition, because this is a condition we later want to change, namely that basically we want the function, the growth of the function is asymptotic to the growth or decay rate of the superlevel sets. And under this condition, we get the following result, namely we get that if we look at the sum, the Birkhoff sum, and now we add additionally these many terms. This is the ones we had before in our second setting, but then we again remove the maximal entries, and we remove some constant times this number m, basically the constant which is attained on this set x without e. And this converges almost surely to some constant. So we get the strong law of large numbers basically using both methods we had before, namely we use trimming and we add additional summons. Okay, if we additionally have the condition that basically the growth of t and the growth of the return time of the return time function are somewhat independent, then we can simplify this strong law of large numbers a little bit and get that, okay, we look at this extended Birkhoff sum, but now we only have to remove the maximum term of the largest value and c times this number m. And it's also valuable to say, to mention that now we divide by n, which well usually, okay, if we have an infinite measure set, then we have to divide by something smaller than n. If we have a finite measure set and a non-integrable observable, okay, then we have to divide by something larger, and now this basically balances each out exactly. And one reason for this is basically that we had this one particular okay, I want to say something before. So if we look at the backward continued fraction transformation, then we get the precise limit law also for the backward continued fractions. So this is exactly, we could exactly apply our system to this setting and sum over the backward continued fraction and then delete possibly other terms and get a precise convergence to 3. And well, if one looks at even integer continued fractions or odd continued fractions, then one basically gets similar results of the same type. I'm not completely sure about the constants anymore, but from the idea, it's exactly the same. And well, I already started talking about it. So here we have this constant n and saying basically these two components, the infinite measure and the non-integrable observable, basically in terms of the norming constant balance each other out, but this is a little bit due to this very strict condition. So who says that? I mean, this is for me, this always felt a little bit artificial that we have to have exactly this condition, and we want to weaken it a little bit. And if we assume that the decay of the measure of t being larger than n is in little o of n, then actually this adding these additional summons is no longer necessary. So basically in this situation, even though we have an infinite measure, the non-integrable observable plays the leading part. On the other hand, it's even possible that if mu of t larger than n is very small, but t is still not integrable, that we even get a strong law of large numbers without doing anything. On the other hand, if now the measure of the super level sets are very small, then one might need to trim additional large entries. So one might even need to trim a number which depends on n. So this is a little bit also in the spirit of what we had in the finite measure case. And lastly, I introduced you to two different settings, basically the dynamically separated sets and the setting where we have a non-integrable observable and a finite on a finite measure set and infinite measures. So why did I actually do this? So I wanted to give you some relations. So I can give you an example of the Romic map. This map here has an indifferent fixed point here and an indifferent fixed point here, and one could also show that okay, we get this same dynamically separation condition, and well, then we can do some inducing, and usually one induces on a set which is of finite measure, but we might actually induce on the set 0, 1/2, and so this is actually a set which has infinite measure. So we basically induce on, if we remember this system of dynamically separated sets, this infinite measure set A united with the finite set Y. And then the transformation we then obtain is the odd-odd continued fraction expansion. And the return time function actually gives us the digits of the odd-odd continued fraction expansion. So this basically throws us back to the situation we just were in a system that we have a non-integrable observable, even non-integrable on a finite measure set, and an infinite measure. And well, we can also alternatively induce on the set 1/3 to 1, and then we basically get the same situation for the even integer continued fraction expansion. And we are again in the same situation as before. And well, as said, both systems fall exactly into the last setting. I mean, I would still like to look at this a little bit further, because maybe these results for the dynamically separated sets and these systems which are basically induced on one of the infinite components could give some relations, but I haven't done that yet. And well, I think I'm also pretty much on the 47th minute, and Claudio will be very happy that I stay in time. And so with that, I would like to close and thank everybody for their attention.
Thanks, Tanja. So also for being in time. So are there questions or comments? So I would just then ask if you can say something more about this separated set. I'm not sure that I really understood what kind of behaviors you can.
Yes, let me just go back. Sorry, it's a bit boring now. Well, I mean, so this is a very nice example to look at. And so what you could look at is basically an indicator function on B or an indicator function on A, and asking, okay, if you look at the Birkhoff sum of the indicator function of B, which distributional laws do you get? And in this case, this is a bit boring because, well, the tails on the left-hand side and the tails on the right-hand side are just the same, but you could bend these tails a little bit, and then you get other limit theorems. And, well, I mean, Jon is here, and who can tell you certainly a little bit more of these limit theorems. And there's a lot of work by Max Thaler and Roland Zweimüller, who looked on more precise limit theorems you get for those kinds of questions. And
Can you say something about, can you say anything about strong laws?
Of strong laws, no, but of weak laws. Basically, if you look at the occupation time of A, if you look basically if you say like something about the Birkhoff sum of indicator function A over indicator function B, if these things are the same, I think, then you get a weak law. But I have to look them up again. They're actually very nice results, but I can't remember all of them.
Okay, so for the moment you only looked at limit laws. You only looked at distributional behavior, not at
Yeah. Well, I mean, it would be nice to also have some strong limit laws, but there is this thing of time in academia. It's always too short.
Okay. No, fine. It was just to understand better. So are there other questions, comments?
Yeah, I'd like to ask something.
Yeah, sure.
Yeah. So how much, it's a basic question, how much distributional chaos can you eliminate by trimming sums?
What exactly do you mean by distributional chaos? You mean like
stochastic process, and I normalize it with something and I get it converging to some stable of order alpha or something, non-trivial distribution, and you tell me you can trim it and get a strong law.
Well, I mean, I have an abstract result. I mean, we can discuss this another time. But basically, if you have a finite measure set,
Yeah,
and an ergodic transformation, not more, and you have a non-integrable observable, you can always get an intermediately trimmed strong law, meaning that you can delete a number of large entries, which might depend on n, but is in little o of n, such that you get a strong law of large numbers.
yeah, okay.
And then, I mean, basically it depends on the system, like on your transformation T, how nicely this, I mean, how many mixing properties you have, and on your tails of your observable F, how large this number actually has to be. So, I mean, in the worst case, it can be something like n divided by log n. I mean, it can be very close to n, but it is still in little o of n.
Yeah, okay.
Okay, so I don't see other people asking for questions or comments, so maybe we can have a small break and I think we resume in 6 minutes for the next talk.
Thanks.
Okay, thanks again, Tanja. From the break. So it's a pleasure to have Jon Aaronson from the Tel Aviv University. He kindly accepted to give us a talk about some of the problems in infinite ergodic theory. So,
Can you
Jon?
see my beamer?
Yeah, we can see part of it. It's
I can
full
see it.
screen. Okay, you have to scroll, but it's not full screen.
Yeah, now we can see it. Yeah. Okay, so welcome to the exercise class for Tanya's talk. As is usual with exercise classes, there will be maybe some connection with what the class was talking about, and maybe not. So what I did was I prepared 3 topics with some questions, which are mainly questions that I don't know how to answer. Maybe you do. If you do, say so. The last one may have some classical problems. So let's start. So we're looking at a conservative ergodic measure-preserving transformation.
Oh, sorry, Jon, we don't see the full
You don't see the full thing.
slide. We see also only half of it. Either you just zoom out a little bit or check
That good?
full screen.
Now we're good. So I mean, measure-preserving transformation, you can call it conservative and ergodic if for every non-negative measurable function with positive integral, you take the Birkhoff sums, and they tend to infinity almost everywhere. So this covers conservative, because if I took the indicator function of a set of positive measure, this would mean that I come back infinitely often to the set in particular. And if I had an invariant set of positive measure, this would mean that it was the whole space, because it would be infinity times, this would be n times the indicator function. This would be going off to infinity almost everywhere, so that means it's got full measure. So we have this kind of thing, a ratio ergodic theorem, that if I take the ratios of the Birkhoff sums, then they behave the same almost surely at each point. So that's the ratio theorem. This is Hopf, or I think this is Stepanov. Hopf did it for the case when conservative but not ergodic. So for an infinite measure preserving transformation, I mean, I could take f. I mean, you could take p to be f to have integral 1, and p to be the, or f to be the indicator function of a big set, and then this would tend to something big, and the reciprocal would tend to something smaller, will be bigger than 1 over n times SNP. So this would give me little O of n. One of the
Sorry for interrupting you, but still I can always see the upper part of the slide. I don't see the statement of the theorem, of the ratio ergodic theorem.
You don't see the statement of the ratio ergodic theorem. So I don't know what to...
You probably, if you go view in your window, go to view option.
View options. I mean, I just kind of, get out of the thing.
No, but just say if you use your view options, probably you can go.
I have chat, notes, reactions, disable, annotation.
No, share is fine. No, but in your window, you have this view option here on the left upper.
I have at the bottom the remote control, annotate, pause share, new share, participant, video, mute.
You can see the full slide.
Yeah.
On your screen. Okay, we only see half of it. So
you see up to it. So you see my cursor?
You can see your cursor, but the window, the slide doesn't move up and down. It's fixed, and we only see the upper part.
This part you see?
We see that you change the slide, but we only see the upper part of each slide.
Like that?
Yeah, still half. Only.
What do you see?
We see up to x by x, while we don't see below.
Up to there, yeah, that's what I see too. So let's see if I can move that. Oh, yeah, right. Maybe I can move that.
Maybe if you go down.
Are we okay now?
Oh, I'm afraid no. If you go down with just in the slide, no, please. I don't know. Maybe try to zoom. Yes, change the zoom.
How about that?
Okay, if you do that, we see the slides moving. Okay, now
Can I make it smaller?
now it's smaller and we can only see. Yeah, I think that's fine.
Okay. So the
Okay.
next, okay, so we got this thing that we have these weakly wandering sets. If you're dissipative, then you have wandering sets. But if you don't have a finite invariant measure, then you have sets of positive measure where subsequence of translates a disjoint. And this is always the case. And there's a problem. This will create problems with all kind of analogs of, shall we say, nice properties. Okay, most things we know, as Tanja showed us, most things we know about infinite measure, we get by inducing on sets of finite measure, and we look at towers. So these towers are kind of called Caputani skyscrapers. So I have what you call n-valued ergodic stationary process. So that means it's a ergodic probability preserving transformation and a measurable function. And then you define the skyscraper in this kind of way. So you draw lots and lots of lines going up as high as phi of x. And then you climb up until you see the sky, and then you jump down and you go to tau of x. So that's the, how you say, the picture of it. And the definition is that you define x to be xn, where x is in omega the base, and I take 1 less than n less than or equal to phi x. And a cross n is going to be the measure, the new measure of a. And txn is going to be tau x1 if n equals phi x. So if you're at the top, you go to drop down to the bottom and go to tau of x. And otherwise, you just climb up. If I had an invertible transformation, then any invertible transformation is actually isomorphic to a skyscraper of this form, where you take any measurable set with finite measure and you define the return time function in the induced transformation in the usual way. Otherwise, T will be a factor of the tower if it's not invertible. Okay, so first thing, we call it pointwise dual ergodic if there are normalizing constants, which we call a return sequence, so that if I look at the transfer operator, so the dual of T restricted to L1, then this converges pointwise to the integral. So this is kind of happens quite a lot. The original was invented by Darling-Katz. They wanted to prove certain theorems, limit theorems, which were normally proved using assumptions of independence, and they wanted just to prove it using ergodic assumptions. And they needed to assume that you had what's called a Darling-Katz set. So there's some A, so that if I take F equals 1A, this convergence is uniform on A. Okay. So no invertible transformation is pointwise dual ergodic because Sn px divided by An for any sequence and any p in L1 plus is never equivalent to 1. Either the lim sup is infinity or the lim inf is 0 or both. If I have a pointwise dual ergodic transformation, because it does not have an invertible factor, an invertible sigma finite factor, so by a result of Parry, the natural extension will have countable Lebesgue spectrum. So it's kind of got a mixing condition, but the mixing condition is somewhat deceptive because it could have eigenvalues. And it's also weakly rational ergodic. This is a weak version of this, so that you have a dense hereditary ring. So that means it's a ring of subsets. Hereditary means it's closed under taking measurable subsets, so that you have this ring. So this will be true for every A and B in this ring. Okay. For example, we could take a Markov chain. So the main example for this talk is going to be Markov chains. And they illustrate, I think they illustrate the problems quite well. And anybody's welcome to generalize anything you know about Markov chains. You can usually generalize to suitable smooth transformations. Okay, so we call this is a measure-preserving transformation. So you have a shift. If we look at the one-sided Markov chain, so you take a countable set, state space S, look at all one-sided sequences, look at the shift, and you take as a measure the Markov measure. So P is a stochastic matrix, and mu is an invariant distribution. Could have finite total sum or infinite total sum. You call P irreducible if from every S and T you can go in some time from S to T with positive probability. That's irreducible. And this is going to be ergodic if and only if P is irreducible. I took the one-sided shift, so I could be ergodic and dissipative. It's conservative if P is recurrent. In other words, the expected number of returns to states is infinite for every state. Anyway, you can calculate the transfer operator of one of being at a certain state at time z1. X is equal to this guy. So it's actually constant on the set S. And so each cylinder like this is a Darling-Cat set. And T is pointwise dual ergodic with the return sequence of this form. Return time process is going to be Bernoulli. In other words, I look at the phi and I look at Ts to the n. These are independent, identically distributed random variables. So we can't do much better than that. Okay, so that's basics. And now we get to the first topic. So first topic, I want to do distributional limits. So we have a measure space, and we have a polar space. And we have kind of measurable observables, if you want, from X into Z. And we take P, a probability on X, which is absolutely continuous with respect to X. So all my measure spaces are going to be standard. So they're Polish spaces with some Borel measure, sigma finite Borel measure. So now we take Y should be a random variable on Z. And then we say that Fn converges strongly in distribution if the P distribution tends to the distribution of Y for every P in probability, which is absolutely continuous with respect to N. Okay, so this kind of is a strong distributional limit. And this sort of thing, I think, goes back to Renyi in certain situations. The fundamental theorem is Egelson's theorem in 1976, which is published in English in a Russian journal. So you don't need to look for a translation. So it's actually undergone various tweaks and refinements. So there's Taleb Sveinmuller 2006 that did something, and I think Wiesel has done something as well. But I don't think my impression is that we're nowhere near the ultimate statement of Egelson's theorem. But anyway, that's what we need today. So if I take Fn, I have an observable like this into Z, and I suppose that the distance from Fn to Fnt tends to 0 in measure. So that means with respect to absolutely continuous probability measures. And Fn tends in P distribution, so the sum P, absolutely continuous P, then it converges for all. So the idea is that if I take, what do? I choose a bounded continuous function on Z. I look at G of Fn. G of Fn is, bounded function in L infinity. So there are subsequences which converge weak star in L infinity. And because of the condition, these limits will be invariant, and so they will be constant. But I know what they are because I already know them. I already had that it converges for one particular measure. So there we go. That's it. That's Egelson's theorem, basically. Okay. So now we're looking at two different kinds of observables. So I'm looking at something equipped with some kind of normalizing sequence. I mean, let's call them a return sequence, but we're not saying that we've got any kind of rational ergodicity at all. We're going to define for a positive L1 function, or non-negative L1 function, two observables. There's going to be the marginal observable, which is just the normalized number of visits to, or the normalized Birkhoff sum of F divided by AN. And this is going to be something in 0 and 50. And we find a process variable, which is going to be a non-decreasing function. So this will be a non-decreasing function, which is right continuous on 0 infinity, which could be looked at as a kind of radon measure on the positive, the interval 0 infinity. Okay, we're going to topologize this with a weak topology. So it's not a Banach space, but if you can get a Polish metric on it. So this is a Polish space. Polish convex linear space. So there it is. I mean, we're looking at these guys, and we say that both of these FNs, they satisfy the condition, the Egelson's theorem. So there's one more thing. These two guys satisfy something a lot better than Egelson's theorem. First thing is that if I have convergence, distributional convergence for one L1 function, then by the ratio ergodic theorem, I have it for all L1 functions, which are non-negative and positive integral. Okay, so we know something about the observables. Now we should look at the normalizing constant. So this sort of rocket limit was first considered, I think, in the 60s by Lamperti. He was also looking at dynamic separation, but not in this context. So if I have some random distribution function, random distribution function on the positive reals, and this CANT tends to C, some guy in L1 plus, then in fact there's some gamma in 0, 1, so that the normalizing constants are regularly varying with index gamma, so like this. And C, the limit process, is C self-similar, so gamma self-similar, which means that if I renormalize the process, the distribution function, then it has this same distribution as C. Okay, so that means that, as I say, if I define this guy as a measure-preserving transformation, it's a measure-preserving transformation. If I happen to have a finite guy, finite invariant measure, then I would have that the increments would also be stationary. So that's called stationary increments. So we have a lot of information for the functional convergence of distribution functions. Things are quite nice for those, relatively simple, but information on normalizing constants for marginal distributional convergence gets a lot more complicated, and you can check out paper of Wiesel from 2018. Okay. So how does one go from distributional limits? So I want to have this kind of idea that I have a conservative ergodic measure-preserving transformation, then I induce and I get a return time process. And maybe I can do something for the return time stochastic process, or maybe I can do something for the infinite guy. So there should be something going on, maybe. So suppose I have AN is gamma regularly varying with gamma with positive index, not with 0 index. Then I can invert. So in other words, SNT1 omega tends in distribution to y, strongly in distribution to y, if and only if the partial sums of the return time function, but now normalized by the inverse function, converge to 1 over y to the power 1 over gamma. So this is gamma regularly varying, and this is 1 over gamma regularly varying. So you could think about this guy going to stable of order gamma, which would be like that. If I'm looking at process limit, so I have C, random distribution function, then I just do the inverse of the process. So c minus 1 of t is infime of s bigger than 0, cs bigger than t, and this I will get. And in fact, it uses Lamperti's theorem. Lamperti, one way to prove Lamperti is to use number 1 here and number 2. Not Lamperti, but what can we do here? Yeah, this has some kind of non-trivial probabilistic behavior here. You can get representations of stable of order alpha in this way. Okay, so the next thing, yeah, okay. So the next thing, the most famous distribution of limits for infinite measure, there's Mittag-Leffler limit distribution. So in fact, I once gave a talk about this distribution at the Mittag-Leffler Institute, and the people there in charge, I mean, the hosts, they told me that Mittag-Leffler was not a probabilist. They were very careful to point that out. Okay, so I have pointwise dual ergodic transformation with the return sequence, which is gamma regularly varying, with gamma in 0, 1. Then you get that SNF over AN tends to the integral of f times y gamma. Y gamma is some random variable, positive finite, for every f in L1 plus. And in fact, also here I have that CANF tends in distribution to a process, M gamma. So M gamma is going to be, so this is, I'm only stating this for gamma bigger than 0. So if you look at the stable subordinator with stationary independent gamma stable increments, so that's a gamma stable increment. So the Laplace transform is constant e to the minus constant times t to the gamma. And y gamma is going to be Mittag-Leffler gamma 1. And Mittag-Leffler is the inverse of the stable subordinator. Y0 actually has an exponential distribution, and you could stretch it by saying that the Mittag-Leffler of order 0 is just a constant. It's a constant process which is just given by one exponential random variable. And when you look at these guys, you're normalizing something by something slowly varying here, so it doesn't matter what t is, right? All the t is going to stay the same. Okay. Yeah, so the proof, I mean, you take a nice omega with omega equals 1, so that could be a Darling-Katz set or what's called a uniform set for the pointwise dual ergodicity. So uniform set could mean that this convergence is uniform on omega for some f. That would be a uniform set. That's another kind of nice set. And you're going to be getting that you can estimate these guys, and you can see that these guys are actually tending to the moments of the Mittag-Leffler function. In fact, these are the coefficients of the, so this is p factorial times the coefficient of the Mittag-Leffler function. The Mittag-Leffler function is the moment generating function of m gamma 1. Okay, we're all okay so far? So far, so good?
Are there comments?
Okay, so I will continue. Yeah. Okay, so here's some questions arising. So question arises, what are the ergodic limits? So what limits do you get? So for each y, which is a random variable, you can find a of n, which is one regularly varying and a conservative ergodic measure preserving transformation. So that SNT of f divided by an should tend to y, of course, times the integral. Yeah. So using Fervat, a result of Wim Fervat, the what you call it, the functional, the process observables tend to y, the same random variable y times the identity function. So actually, if I go back to this, the identity function, if you look at the Mittag-Leffler process for the stable, one stable subordinator, the positive stable subordinator with index 1 is just a constant. It's just the identity. So I do the inverse, I get the identity. So Mittag-Leffler of order 1, M1 of t is equal to t. Okay. So we want to put C in random variables, random distribution functions, an ergodic, gamma ergodic limit. If there's a conservative ergodic measure preserving transformation and a regularly varying sequence, gamma regularly varying, so that you get MF gamma, MFC for every FNL1 plus. So you look at the collection of ergodic limits. And all I did with Benji was to show that the one ergodic limit set is everything. Everything times the identity process. By the Darling-Katz theorem, which we had before, the ergodic limits for gamma contains all positive multiples of Mittag-Leffler process. And the question is if there's anything more. So that's the first question. So that's it, actually. That's my question on distribution limits. Can you find anything more? So if nobody's got any answers, we can carry on to the next exercise, yeah? So next one, we want to look at mixing properties. So most famous mixing property, there was an example of Hopf in his book in 1936 of a mixing transformation, what he called a mixing transformation. And afterwards, this was kind of developed by Krickeberg, so it's now called Hopf-Krickeberg mixing. So what you have a measure-preserving transformation, and you have a ring which is invariant and generates the sigma algebra. So it's a ring of sets of finite measure. And then you say it's mixing, mixing, if there's some normalizing constants. So that measure of A intersect T minus NB divided by UN tends to measure of A times measure of B for every A and B in R. So, first thing one sees here, that if you had A equals B equals a weakly wandering set, this is not going to be possible. Yes, this is going to be positive eventually, but it's going to be zero infinitely often if I had a weakly wandering set. So since every set of finite measure contains a weakly wandering subset, you're not going to get this with a hereditary ring. Hereditary ring meaning that it's closed under taking measurable subsets. So on the bright side, if T is HK mixing, then the UNTs tend to 0. So this means that the Koopman operator of the natural extension is what we call mixing. The spectral type is what they call a Rachman measure. Fourier transforms, Fourier coefficients tend to 0. Okay, so this is mixing properties if you want integrated mixing. Now we're going to go for ratio limits and conditional mixing. So we've got a measure preserving transformation, we've got a transfer operator, so we can ask for conditional or pre-image mixing in the same kind of way. So the first thing we do is say it's got ratio limits if there's some normalizing constant, so that T hat n F divided by UN tends to integral of F for every F in some collection where the closed span is equal to L1, should generate L1. So if you had that it contained the indicators of some sets in a ring, which is a generating ring, then we would call T conditional HK mixing, CHK mixing. Okay, so what's going to happen? So we look at an irreducible recurrent Markov chain that we had before. Then we can do HK mixing, the previous kind, with R to be the ring generated by cylinders, if and only if you have what's called the strong ratio limit property. So for every S, you have that PSS n is asymptotic to PSS n plus 1. So it's the basic result. For certain intermittent interval maps, there's a lot of work from Thaler and Melbourne to Hesiu. So then you have the same kind of thing, that you have R is finite measure Riemann integrable set. So you take an intermittent map with a infinite invariant measure. Finite measure means you're going to be Riemann sets or bounded away from the fixed points, the indifferent fixed points. In both of these cases, HK mixing is the same as CHK mixing. Okay. So now we get to measure theoretic properties. So basically, we had this problem of weakly wandering sets that we can't really say anything about. We can't say much measure theoretically about these guys because we can't have a hereditary ring. So how do you get around that? You say, well, I'm going to do rational weak mixing. And so here's the definition of rational weak mixing. So I have conservative ergodic measure preserving transformation. It's going to be rational weakly mixing. If the sum F, so that 1 over ANF, so ANF is going to be the sum of these UNFs, and these UNFs are what you would use for the mixing. And then you look at measure of A intersect T minus NB minus UNF, these normalizing constants, times the measure of the product. And this should go to 0 as n goes to infinity. So it's like the measure of T minus N, A intersect T minus NB divided by UNF, converging in some kind of strong Chisaro way, generalized strong Chisaro way, to the product of the measures. So we can get that rational weak mixing implies weak rational ergodicity, because strong Chisaro implies weak Chisaro convergence. And in fact, this guy will hold for every F in the hereditary ring for weak rational ergodicity. Rational weak mixing implies spectral weak mixing. That means no L infinity eigenvalues, but not conversely. This is irritating. So in fact, you can have rationally ergodic, you can have a rationally ergodic rational weak mixing transformation, spectrally weakly mixing transformation, which is weakly rationally ergodic, but not rationally weakly mixing. Rational weak mixing does not imply mixing of Koopman operator. So Cesar Silva and some co-authors in 2015, they created a kind of rank 1 transformation, a generalized Chacon transformation, which has positive type. In other words, the spectral measure of the spectral measure is not a Reichmann measure, it's spectral type. Okay. So now we're talking about conditional rational weak mixing. So here I have the same kind of thing, but with respect to the transfer operators. Conditional Hopf-Krickeberg mixing implies pointwise dual ergodicity. Sorry, this should have point. There should be a pointwise dual ergodic transformation, which is Krickeberg mixing, should be conditionally rationally weakly mixing. And this, in turn, will imply rational weak mixing and pointwise dual ergodicity. So I'm not going to get pointwise dual ergodicity free from conditional HK mixing. Okay, so here's a question. So now we knew that, now we've got a transformation which is both pointwise dual ergodic and spectrally weakly mixing. Is it true that XMT is rationally weakly mixing, or even better, is it conditionally? So let's test this out, see what we know about Markov shifts. So we have a irreducible recurrent with stationary distribution mu. The one-sided shift you're rationally weakly mixing if and only if you're conditionally rationally weakly mixing. If the sum and hence every S, you have this kind of smoothness condition of the renewal sequence. If you remember, we had the strong ratio limit property if there was, this was asymptotic, yeah? So, in a certain case, if the return sequence of the Markov chain is big, so it's the partial sums of ANTs is the partial sums of these PSSKs. If this is bigger than some constant times root n, and T is spectrally weakly mixing, in other words, this renewal sequence is aperiodic, then C will be conditionally rationally weakly mixing. So the proof uses a result of Gomilko-Tomilo from 2018. If you have an aperiodic renewal sequence, UN minus UN plus 1 squared is finite. There was actually a conjecture of, I think, Erdos, De Bruijn, and later by Kingman, that you could put the absolute value here instead of the square. Just mod UN minus UN plus 1. But there was a counterexample by Ibragimov. But still, we don't know that this is not generally true. So that's the... So this question is even open for Markov chains. Okay, how much longer do I have?
Maybe I can ask if there are questions also. At the moment, questions from the audience?
Can't hear
Can
you.
I ask a quick question? Sorry.
Sure.
So John, you mentioned that conditionally of Krickenberg mixing implies conditionally rational weak mixing.
Yeah. Together with Weiss-Juhl logicity.
And do we know examples where the system is conditionally rationally weak mixing, but not strongly mixing, as in?
No.
The counterexample to the reverse implication to this.
Conditional rationally weakly mixing, but not Krickenberg mixing, you mean?
Yeah, exactly.
Do I know examples of that? There are examples. I mean, there are examples of rational weak mixing, which are not Krickenberg mixing by Cesar Silva. Yeah. But I don't know. No, I don't know that.
And do we expect, I don't know if that makes sense to the question, but do we expect the typical infinite measure preserving transformation to be rational weak mixing, but not Krickenberg mixing?
Depends how you want to look at your infinite measure preserving transformation. So
yeah.
The usual kind of thing is to look at invertible guys with a weak operator topology, and then you have a conjugacy lemma. So every strange property contributes a density delta on a subsequence of this property. Yeah. If we look at if we want to look at these adjoint guys, so we want the transformations should converge in weak operator, and also the transfer operators should converge, then there are possibilities to get something interesting. That's a different question. Yeah. So, for example, for finite measure, if you look at this, what they call strong adjoint topology, then you get exact endomorphisms are residual. That's Parry, Walters, and a student called Rachel Palmer.
Mm-hmm.
So it's got some kind of there's some kind of hope with infinite measure there.
Thank you.
Yeah.
Okay, so we are a little bit over time, so maybe we can go through this last question quicker.
You want me to go through it quickly? Okay, so here we go. We're looking at multiple recurrence. So you've heard of this. You call it measure preserving transformation D recurrent. If for every A with positive measure, there's some N so that these guys are positive, have positive measure. So it's easy to see that this means this is D recurrent. This is D recurrent if and only if for every A with positive measure and almost every X in A, the sets of visits contain arithmetic progressions of length D plus 1. Furstenberg and Semerady in the 70s showed that probability preserving transformations are multiply recurrent. In other words, D recurrent for every D bigger than or equal to 1. So they also showed that So Semerady had a combinatorial proof, and Furstenberg had an ergodic proof, meaning that if you take a sequence of positive density, then you can embed this in some probability preserving transformation and then prove it that. There's the Erdos conjecture. So here's the combinatorial one. If I have K, some subset, and it could, something like the primes maybe, the sum of the reciprocals is infinite, then K should contain arithmetic progressions of arbitrary length. There's an ergodic Erdos conjecture, which says that, so if I take function in L1 plus, and I look at this sum, and this should be infinite almost surely. So you can see that because n is 1 over n is monotone decreasing, it's a super invariant set or something where it's infinite. And so this will be invariant set, so it'll be constant, either finite or infinite almost surely. And by the ratio theorem, it will be the same for every L1. So this is the same thing as saying, it's equivalent to saying that T cross a simple random walk on Z2 is conservative. And the question is if this implies that X and T is multiply recurrent. So without solving, this is the big question, can you solve this? There's another question, there's some side questions. Does the ergodic Erdos conjecture imply the combinatorial one? So at the moment, we have no way to embed these sequences into some infinite transformation, satisfying this. The other question is, what about other configurations? So if the conservative ergodic measure preserving transformation is D-recurrent, is it strongly D-recurrent? So here's a sense that I could take other, other configurations, any A1, A2 up to AD, natural numbers. Does there exist an N so that this intersection is positive? No idea. Okay, so for nice guys like Markov chains and other things, so we could call the transformation D-rationally ergodic if there exists ADN up to infinity, a dense hereditary ring, so that these guys, sums of these guys, so it's like taking the multiple sums, and they should tend to the product of the measures for every B0 up to BD in the hereditary ring. And you call it D-rationally weakly mixing if the convergence is strong Chisaro. So what we know is D-rational weak mixing, just like with the situation with D equals 1. This implies D-rationally ergodic, implies D-recurrent. The reverse implications are wrong. So there's a question now. So this is related to what we asked about Markov chains. Does one rationally weakly mixing and D rationally ergodic imply D rationally weakly mixing? That's a question. So for Markov chains, what we know is that if the conjecture is true that it's as soon as it's weakly mixing, it's rationally weakly mixing, then this would be true for Markov chains. Okay, so here's multiple properties of Markov shifts. So you take a Markov shift and it's going to be D-recurrent if and only if the D default Cartesian product is conservative. In this case, if it's ergodic, then it's going to be D rationally ergodic. And if P also satisfies the strong ratio limit property, see there we've got it coming in again, then I know that T is D rationally weakly mixing. So the sequences are like that, and the hereditary ring satisfies that you should be contained in some cylinder. So here's a corollary of what we have. The ergodic Erdos conjecture holds for Markov chains, in fact, more holds. So you have the renewal sequence and you divide by n to the r, and this should diverge for every r in the open interval 0, 1, not necessarily including 1. Then you should have the T is your Markov shift is multiply recurrent. You can find Markov shifts where the classical Erdos condition fails. But this actually nevertheless is true for Markov chains and other what we call nice transformations. In general, there's a not so nice transformation, so that it satisfies this condition for every r between 0 and 1. but it's not too recurrent. So in other words, there are no arithmetic progressions of length 2 for some sets there. Okay, so that's it. Since it's infinite, this is my infinite slide, and that's it. Thanks for listening.
Thanks, John. And let me clap you for everybody. So are there other comments or questions, of course? Questions on the questions or answer to the questions? Can I just ask a quick question about the last statement, actually? So you said that in principle, when you have a result for Markov chains, you expect it to be true also for nice systems. So you said this is true also for in this case, if I understood correctly. So what are the nice systems for which you know this?
Nice systems. Yeah, basically, okay. So Markov chain means that I can induce, what do I get? It's a tower over a system of IIDs. Yeah. When I induce on some state and I get what's called a fibered system where everything's independent. A nice system would be Gibbs Markov.
Oh.
That's something Gibbs Markov. So you have these nice intermittent systems. I mean, you know what kind of things you get there. Question is, how far can you go? Can you need it to be, you want to have these funny young towers or something? I mean, there's work to be done there.
So you need quick mixing for the inducement.
Yeah, so the conjecture would be that, you're weak mixing. Where are we? Yeah, certainly you need weak mixing. Because I want the Cartesian products to be rationally weak mixing, yeah. So the usual kind of thing is, so what goes on with this kind of thing? You have some hopes, because you have tower over Gibbs Markov, you have local limit theorems for maybe the height function. And so there you can get, you get a local limit theorem, a conditional local limit theorem. So you can actually iterate conditional rational weak mixing. Or conditional, yeah, you can iterate conditional Cricket-Berg mixing. That one can do for these things. So you've got these guys converging and they converge uniformly, and then you just do another time. So you've got t hat of n, and now you do t hat of 2n and t hat of 3n and blah blah blah, as many as you want. As long as it takes, it should be conservative. You should still be with the same kind of thing. But further than that, no idea.
Okay, so it seems that it's okay. Are there other questions, comments? Okay. Then let me thank both the speakers again, and also take the opportunity to thank both the speakers. Tanja, are you still here? Also, and for your nice thoughts. And so, goodbye, everybody, and we hope to see you again at the next DAC seminar.
Okay. Yeah.